Dr. S. Shankar is a professor, Department of Physics at Madras Institute of Technology, Anna University, Chennai. His area of specialization is solid-state physics. He has guided more than 10 PhD scholars. He has published more than 50 national and international research papers. He has 28 years of teaching experience.
Welcome to the UGC lecture series in physics. Now we are going to see about the magnetic properties of materials and some more fundamental aspects of such properties. In this lecture, we have the objectives as to study about classical or Langevin theory of diamagnetism and Langevin theory of paramagnetism, which is also classical one, and we have quantum mechanical extension also for the paramagnetic studies. We will see both the type of studies for paramagnetism. The permanent magnetic moment in a material results from the following contributions. First one is coming from the intrinsic spin magnetic moments of electrons, which we had seen that the magnetic moment is arising from intrinsic spinning motion of the electrons with respect to the spinning axis. And the other one is orbital motion of the electrons, and this is all coming from the electrons which are orbiting around the nuclei. And the third one is spin magnetic moment coming from the nucleus, and this nuclear magnetic moment is actually very feeble, and for most of the practical applications we neglect the magnetic moment coming from the nucleus, and for almost all purposes, practical applications, we consider orbital motion and spin motion magnetic moments coming from the electrons. Diamagnetism, Langevin theory. The magnetic moment associated with the orbital motion of electron is related to the corresponding angular momentum L through the relation. So, we start from this definition to go for some mathematical derivation of this theory, that is the angular momentum L multiplied by E by 2m with a negative sign here gives rise to the magnetic moment, or mu equal to minus E by m into L. And in accordance with the Faraday law, we have the following theorem, that is integral of E multiplying dl, where dl is the linear element and E is the electric field, and the integration is over is circular orbit or the current loop, and when this integration is carried out, the result is equivalent to minus d by dt, that is time variation of this b dot ds integral, where this is a surface integral carried over the orbit surface area, and b here is the magnetic flux density, and ds of course is the aerial element. And here if we carry out that integration, what we have is E multiplying 2 pi r. Here we assume that E is constant. If you assume constant energy loop, then E is field is constant there, and so E can be taken outside the integral, and so dl can be integrated to get 2 pi r. If it is a circular orbit, then on the right hand side in the same way B is constant and ds is the surface area. So, this is circular area, so pi r square we get, and so then d by dt is there, then we can integrate here and get. So, since pi r square is not varying with time, b will vary with time. So, we take first derivative of b with respect to time on the right side, and here 2 pi r is there, then we cancel out the common terms, and finally we get E equal to minus half R dV by dt. And the situation is explained here in a diagrammatic manner. So we have a magnetic field here and a looping current or looping electron, and so we have this the radius vector and so on, and magnetic field is applied here. So we have one electron considered here. Then if this is the case, then this will go up like this, and then you get the magnetic moment going up. Now the induced electric field exerts a torque also upon the electron, as we have seen here. So there will be a torque because of this tilting of this orbit, and hence we get the torque, of course, is equivalent to minus E into capital E into R on the electron, which in turn produces a change in angular momentum in accordance with the equation tau equal to dl by dt. This is a torque expression. Now we can write for this L, E into, so for capital E we substitute here, and so we have this one, and minus minus will cancel, and then on the right side we have dl by dt. Now the change in angular momentum del L of an electron during the magnetic field changes from 0 to B is obtained by integrating the above equation. That is, when we start applying the magnetic field, then it goes from 0 value to B over time period, and so within that time period the angular momentum changes, and this change has to be obtained by integrating the above equation. So here, then if you do that, then this dl after integration can be represented as change in angular momentum del L, and this can be seen to be equivalent to this half ER square B after integration. Dt will cancel, and so this will simply become B here, and that is it after integration. R square will remain here, E is there, plus, so half remains, and so on. This is straightforward integration and cross multiplication. Then this change in angular momentum develops a change in magnetic moment given by del mu equal to this expression we have seen, mu equal to minus E by 2m into L, but in place of L we write, in place of L we have del L, and so corresponding change is del mu, and that is equivalent to, we write for del L here from the above equation, then we get finally E square R square by 4m into B, and that is for a single electron, and for all the electrons in an atom we can sum over here, and for all electrons B is common, but R is not common, the orbiting radius is not common. So if you sum over this quantity for all electrons, then here for every electron the orbital radius varies, and hence the summation has to be carried out for this R, and we put an index here I to represent the electron, and so if we have Z number of electrons, then this should be summed over for all Z electrons. So we have this one where Z is a number of electrons in the atom. Then we can write this summation over Ri square as sum over R square, that is average square value or average radial square value of an electron in an atom, and this is obtained as follows. So for any orbit radius, this with the radius rho, we have rho square equal to x square plus y square plus z square, like with a sphere. Then, and also for isotropic distributions, we will have x square average equal to y square average equal to z square average, and that is equal to 1/3 of rho square average. and these are spherically symmetric averaging out quantities, and for 2 dimensions we have r square equal to x square plus y square equal to 2 by 3 rho square. This is all for spherical, but what we consider here is a plane, and so for 2 dimensional case that is a circular orbit, therefore r square should go as 2/3 of rho square. Now we can write this in place of the r square here, and hence the mu atom becomes minus z square b by 4m into 2/3 of rho square, that is r square average is replaced by this for 2 dimensional case. So we have minus z square b by 6m, 2 to cancel here, 6m multiplying rho square. This rho square is the mean square radius of an atom. Now since there are n atoms per unit volume, the magnetization induced in the specimen is hence equivalent to m, that is equal to capital N number per unit volume, that is concentration, multiplying mu atom. This mu atom is actually for a single atom, right? And so if we have n number of atoms per unit volume, then magnetization by definition is given by the magnetic moment concentration in the material, that is the total number of magnetic moments along a particular direction per unit volume. So we get this quantity by taking concentration of atoms and multiplying mu per atom, and so we multiply this quantity by n to get n z square b divided by 6m into rho square, but a minus sign is here. Now the diamagnetic susceptibility of the specimen is therefore chi equal to m by h, and here for b we write mu h, and hence you can take this. So finally you will get, that is mu naught h will be there, h will cancel, and finally we get chi equal to minus mu naught n z square by 6m into rho square average. So this is a simple result, and this is in fact, this chi as we had seen is independent of the temperature. There is no temperature factor in this, and these are all coming from the orbiting electrons in the filled shells. Therefore this type of magnetism is there in all materials wherever we have orbiting electrons in filled shells. And so whether it is a metal or non-metal or whatever be the nature of material, all the materials will have this type of diamagnetic contribution to the total magnetism, but this is actually feeble. In an earlier lecture we have seen that chi versus temperature behavior for diamagnetic material is a constant, that is chi is independent of temperature, and that is obtained here now mathematically also. Now we go for the classical theory of paramagnetism, that is Langevin theory. Here actually this paramagnetism is observed in metals, atoms and molecules possessing an odd number of electrons, that is free sodium atoms, gaseous, nitric oxide, etc. One important thing in all these things is that they all have free electrons liberated from their valence shells, and in particularly metals with the free electrons, these electrons move randomly and freely over the entire volume of the material, and these free electrons only contribute for this paramagnetism, and their corresponding spin magnetic moments from each electron are randomly oriented as shown here. So in natural condition, that is in the absence of external magnetic field, net dipole moment is 0, that is mu along any particular direction will be 0, because this positive direction moment is cancelled by the negative direction moment, and so on. This is an example of isotropic distribution. Now, in the presence of external magnetic field, however, they all tend to align along the direction of the field. So, there will be a net moment component along the direction of the field from each electron, and so we can sum over all such contributions along the direction of the field from each electron and obtain the resultant magnetic moment. That is the basic idea here. Now, so dipoles align themselves along the direction of external applied magnetic field in order to have a state of lower energy. The net magnetization of the sample become non-zero and parallel to the magnetic field, and for large magnetic fields at low temperature the magnetization becomes constant for the sample. This implies that saturation is achieved and all the dipoles are aligned along the direction of magnetic field. So, such orientation will become maximum if the thermal agitation is or thermal excitation is absent, and so when the material is cooled down to a temperature close to 0 Kelvin or so, then such deviation or misalignment will be absent for such electrons, and so along the direction of the field there will be a full alignment of all these moments. So, we will get maximum contribution to the magnetic moment. Now, Langevin theory of paramagnetism. Here the theoretical explanation for the same was given on the basis of Boltzmann classical statistics first. So, according to this theory, each atom consists of a permanent magnetic dipole moment mu. That is, the magnitude is this, only orientation differs. Therefore, the component of mu along the field direction is mu cos theta. If you take this one along this, see here when we say field, here we are talking about the magnetic induction or magnetic flux density developed here. So, mu cos theta is along B. So, the energy associated here due to the interaction of mu with B is minus mu dot B, and so we have minus mu v cos theta. So, W expresses the interaction of this magnetic moment with the applied field. Then, in accordance to Boltzmann classical statistics, the number of atoms having corresponding energy or potential energy or magnetic potential energy in the range W and W plus dW is given by some dN equal to some constant d power minus W by kBt into dW. Then we can substitute this W value or W expression here, which is equivalent to mu h cos theta, and dW means then cos theta alone will change, mu and B are constants. So, we write all those things here and then work out a summation procedure. Summation is actually integration process, because the spin orientations are randomly present for all directions theta with respect to the applied field. So, theta can be random for every spin, and therefore, we cannot neglect any theta. Therefore, if we want to sum over all such alignments of mu along every possible theta, then we have to integrate here, and so we carry out that integration here. So, this is what the expression or the integrand, and the procedure is straightforward. So, we get this one. So, C here of course is due to the normalizing factor and so on. C is n by this, and we substitute here. These are all straightforward results which are very well available. This is a direct method in fact. So, we carry out this integration and this integration separately, and then work out for m. So, this is a procedure of evaluating that integration. So, we carry out that. So, numerator integration, denominator integration like this, and then here we go for change of variable. Take mu b by k by t equal to x, and then integration becomes simply m equal to n times mu, where n is a concentration, n times mu multiplying this plus 1 to minus 1 integration of e power xy into y dy divided by e power xy dy integration from plus 1 to minus 1. Here theta value, actually this is something about how we go for the change of limits. When we change the variable from theta to y, then the limits also should be changed. So, here we give how we change those. This explains how we go about the derivation, and see, after integration we get this one, then plus 1 to minus 1 limit we can apply here, and here also, then finally we get this, and so this is all about like this. Then finally we get n mu multiplying cot hx minus 1 by x. This is actually a dimensionless function, and n is a concentration, mu is the magnetic moment per spin, and so we have this. And this m is therefore represented as n mu, where n mu is a maximum value possible. So, this is called as a saturation value. So, ms, capital Ms, saturation magnetization multiplying this function, and this function is known as Langevin function, and here we plot the Langevin function as a function of x. This is L of x as a versus x, and this is a nonlinear curve like this, and we have two limiting cases here. One is near the origin, and the other is near the saturation value. And near the origin, of course, is for high temperature, when x is small, in other words. So, near the origin means when x is small, the x equal to mu b by k by t, therefore, this when t is high, x becomes small. So, this is high temperature limit near the origin, and if you work out like that, then this approximation or this limit is valid only along this region where the curve and the straight line approximation both coincide or both are overlapping. So, within this region, that is at high temperature, we can simplify the expression by expanding this one for small x. So, if you do that, then finally we get this quantity to be x by 3. This cot hx minus 1 by x will go to be x by 3 for small x by neglecting higher order terms x square, x cube, and so on. Then for x, we substitute the previous value. Here we have x equal to mu b by k by t. So, this value we substitute that, and finally obtain m under high temperature limit to be n mu square mu naught h by 3 k b t. This mu here is a value of magnetic moment or magnitude of magnetic moment, and mu naught is permeability, should not be confused here. Now, from here we can get the chi value, chi as m by h. So, if you do that, then the right hand side remains to be a constant divided by temperature. This ms square mu naught by 3 n kb can be taken to be a constant, which is known as the Curie constant, which was mentioned earlier. And so, chi is therefore found to be proportional to 1 by t. And so, the behavior of the curve will be somewhat like this, which we had seen in the previous lecture. Now, we go for the quantum counterpart of the paramagnetism. See here, see in the earlier case, the orientation of spins were taken to be continuous. All values of theta were permitted, whereas here this is not so, because the angular momentum is quantized in quantum theory for the electrons. When the orbital orientation is changing, angular momentum will also change, and this change will be a quantized one, and all will be taking discrete values like this. So, we have orientation quantization and space quantization. This is also called as space quantization. Then the corresponding energy levels will also be splitting, and we have a G factor for this kind of splitting, which is known as spectroscopic splitting factor. And for orbital motion, G equal to 1, and when the spin motion is reorienting, then this orientation will also be discrete, and that gives rise to similar type of orientation for the spin planes, and G is taken to be 2 for such things. Now, if J is the total angular momentum, then this total angular momentum is expressed as a sum of orbital angular momentum and spin angular momentum. This L is the total angular momentum of electrons, and S is total angular momentum of spin. That is, this is total angular momentum of orbiting electrons. Here we should take like that. Then the effective magnetic moment is now given by this, the possible value, that is the magnitudes of J, L and S are all given like this from angular momentum theory. So, if you use all these things, then finally we get mu effective to be expressed in short like this, and this is a schematic diagram representing the orientation of this mu effective with respect to the field. Then mu s is this, and G also has got some expression like this in general, and we can write mu finally in terms of this. Then the W, that is the interaction energy, in terms of G mu b is written like this for jth electron, and we can now go for the Boltzmann statistical function and write W by kBT there with these values and carry out similar integration, and this explains that, and finally work out chi to be like this. So, chi is again obtained to be proportional to 1 by T, that is inversely proportional to the temperature like this, but some numerical values are slightly different, and there are other quantities like P effective, that is the effective number of Bohr magnetrons and so on. Bohr magneton is the quantized magnetic moment value for an electron. Coming to summary, the classical theory of diamagnetism has been studied in the present lecture. Classical theory of paramagnetism has also been studied by using Langevin theory, and the quantum concepts have been introduced in the paramagnetic theory, and their consequences have also been studied. And we have found that the classical theory and the quantum theory both lead to the same temperature dependence of the susceptibility. A few questions here. What type of materials possess diamagnetism? Why? Next is, what is the low temperature dependence of paramagnetism? And distinguish between classical and quantum results of paramagnetism. Thank you for your patient listening.